everyone, I decided I wanted to make a video going through the two practice problems from 15.2 notes since we didn't get to these in class, and 15.2 is a really important and kind of difficult section. So I would encourage you to try and work through these first on your own, and then you can come look here and see how I approached the problem. So in number 2, we're supposed to do this path integral or line integral. This is of a function, not of a vector field, so this is the first type, along the path that we did in this practice problem number 1. So we looked at a lot of different ways to parameterize this little triangle here, and we could use any of those to do this integral, and the answers are going to look different depending upon which one you use. So let me just write out a couple of options, and we can see how those would be different using each approach. So I'm going to call this long diagonal piece the first curve. So one way I could parameterize this would be, for all of these, the x coordinate is going to be 0. The y coordinate and z coordinate are changing along this diagonal one. If I wanted to do t's starting from 0 and going to 2, for example, I could have my y value just be t, since the y's go from 0 to 2 along that diagonal path. And then the z value, what we talked about in class, the equation of this diagonal line is z equals 1/2 y. So if my y is t, then my z would be 1/2 t. And then for the second curve, I might use another vector valued function. If my t again starts at 0, and I might want to go up to 1 here. So this is an approach where I'm parameterizing these two different paths, both starting from 0, and it doesn't matter that they overlap because we're going to deal with these as separate pieces of the integral anyway. So if I go from 0 to 1 here, then again my x coordinate will be 0, my y coordinate is 2 for all the values along this path, and then the z coordinate here is starting at 1 and going to 0. I can parameterize that as negative t plus 1. So when t is 0, that is just 1. When t is 1, that is 0. So this again is one way to parameterize this curve. For the third one, I'm again going to start my t value at 0, just like I did the others. I'll go up to 2 in this case, just because it gives me some nicer numbers. And this is going to be 0. The z coordinate is also 0 here, and the y coordinate could be negative t plus 2. So here, if t is 0, we get 2. If t is 2, we get 0. So it's tracing backwards along that bottom line. So this is one possibility. Here's another way we could do this. I might keep the first one the same, starting at 0 and going to 2. And then if I wanted these paths for some reason to be kind of one right after the other, maybe I start my next one at 2 and go to 3. So here, the x and the y coordinates are going to stay the same because those are just constant 0 and 2. But my z coordinate is not going to be negative t plus 1 anymore. It has to adjust for the fact that I'm starting my t at 2 and ending at 3. So here I could do negative t plus 3. If I plug in 2, I get 1. If I plug in 3, I get 0. And then C3, I might pick up at 3 and go until 5. And the reason I'm picking 5 here is because we're going 2 units along the y-axis in this piece of path, so it's just convenient to have my t value go 2 units as well, but there's no reason you couldn't go to 4 or to 7 or to any other value. So my x coordinate is 0, my z coordinate is also 0, and my y coordinate in this case would be negative t plus 5. Again, if I check this, plugging in 3 gives me 2, plugging in 5 gives me 0, and those are the y values that I want to start and end that curve. So this is just 2 possibilities. There are literally an infinite number of possible paths you could write here. And each one of these options is going to give us slightly different looking integrals. So you just have to write one and then use that for your problem. And the results, the integral itself will look different, but your answer in the end should be the same. Okay, so for number 2, because this curve is 3 different pieces, we're going to have to kind of break this apart where we're going to integrate C1, integrate this function over C1, plus integrate the same thing over C2, plus the same thing over C3. Our domain is essentially broken into 3 pieces, so we have to do the integral in 3 pieces. So for C1, I want to look at what is my path for this. And I'm going to use the ones from this first option. If you use the second option, I'll talk about how that would be a little bit different. So we parameterized C1 with this path 0, t, 1/2 t, from t going from 0 to 2. So I want to kind of put all this information together. My integral, which is going to be with respect to t, needs to have t-bounds, and with this parameterization, my t-bounds would be from 0 to 2. And then the function itself, I can't write 2x plus y squared minus z because that's not in terms of our variable t. So I have to replace each of these variables with what they would be along the path. So 2x is going to be 2 times the x value along the path, which in this case is just 0, plus y squared is in this case going to be t squared, and then minus z is going to be minus 1/2 t. So this is that function kind of converted by plugging in the path values. Next is the ds piece. Remember that ds is going to be the magnitude of r prime and then times dt. So we'll have to work out the magnitude of r prime here. R prime is 0, 1, 1/2. This particular one has derivatives that are all constants, and again, that doesn't always happen, but it can happen. And so the magnitude of r prime would be the square root of 0 plus 1 squared plus 1/2 squared. So that's the square root of 5/4. So in the integral, we're going to have square root of 5/4 and then dt. This integral is what we would need to compute to get that line integral across C1. So next, we're going to do the same thing for C2. So I want to look at what is my C2 path, right? How did we write that? So based on that option 1 parameterization, this was my path. Again, I'm going to have to find out what is r prime. This is 0, 0, -1 in this case. And then the magnitude of r prime here would just be 1. So nice and simple. And then my integral, I'm setting up my bounds, right? The bounds in this case are 0 to 1, since those were the starting and ending t values for that parameterization. And then I again want 2x plus y squared minus z, except I'm replacing the x, the y, and the z with, in this case, 0, 2, and -t plus 1. So that we've got that function times ds, which in this case is just 1 dt. And then the last piece, if I can squeeze this on the screen here, I need to do C3. So I need my path for C3. So here's my path for C3. R prime in this case comes out to be 0, -1, 0. And the magnitude of r prime is again just 1 here. And so that last integral, we're integrating from 0 to 2, converting the function 2x plus y squared minus z by plugging in the components from the path. That's 0, -t plus 2, and 0. And then I have 1 dt. So here's our completely set up integrals. I have to compute each one of these. These particular integrals would not be very difficult to compute if you actually go through and simplify these. For example, the first one, we can take out the root 5/4, and then we're going from 0 to 2 of just t squared minus 1/2 t. So the antiderivative there would just be a simple backwards power rule. You might take a minute, pause the video, compute this integral out if you want, or I'll just come back in a second with our answer. So here we are. I computed each one of these. The first one comes out to 4 root 5 over 3 minus root 5 over 2. The second one comes out to 3 plus a half. The third one comes out to 8/3. None of these combine particularly nicely, but if you plug this into a calculator, you get about 8.03 with some other decimals. So you should get this 8.03 value regardless of what parameterization you did. But if you chose, if I come back up here, if you chose to use, for example, this parameterization, this is going to change not only what the t-bounds are for each interval, but it will also change what you're plugging in for x, y, and z. So the integrals themselves are going to look pretty different, but the answer should come out to be the same. So this is why it really doesn't matter what parameterization you use. You should use whatever the simplest parameterization you can come up with is. So I like to use these ones where we're starting at 0 each time, just because it's a nice place to start. It also makes your integrals a little bit nicer because you don't, when you plug in the 0, it's usually easier to plug in that bound. But either one of these should work, or some other parameterization if you wanted to try one of the ones that you guys came up with in class. Here's the second integral problem. This is number 3 from the notes. So in this case, we're finding the work done on a particle, and so this is integrating not a function, but a vector field. So we're moving along this path C, and in this case, we're given the path. This is not written as a vector-valued function, but they've already parameterized it for us. So this is saying that r of t is the vector cosine cubed of t, and then sine cubed of t. And this is starting at the point 1, 0 and going to the point 0, 1. Now, for the integral, we're going to need to know what are the t values for that. So this is just a matter of, okay, if my x coordinate is 1 and the x is coming from cosine cubed of t, what would t need to be in order for that to work out? So cosine is going to be equal to 1 when t is 0. And if I double check, if I plug 0 into each of these components, I get 1 from my x component and 0 from the y component, and that's what I want. Similarly, 0, 1, if my x value has to be a 0, t would have to be a number like pi over 2, and that would be the first value that gives us the point 0, 1. So I want to do pi over 2 rather than doing, for example, 5 pi over 2, because I don't want this to go around this path, multiple times. If you're curious, try graphing this path as a space curve with our graphing program. This one's kind of interesting. It looks a little bit like a circle, but it's not quite circular. The cube pieces here give us kind of like a square circle. It's kind of a cool path. All right, and then the force field that's doing this work is described by x squared and negative xy. So this is just a two-dimensional force function. And our work is going to be an integral. So our work is going to be the line integral along the path C of our force vector field dotted with dr. I didn't mention this in class, but when you're writing dr, make sure that this is a vector and not just dr with no vector on it. This is a dot product, it's not a scalar product. So when we're setting this up, this is all going to be an integral with respect to t again. So my t bounds are going to be 0 to pi over 2 based on the path that I've got. I need to take my f vector field, which is x squared comma negative xy, but I need to parameterize this according to the path. So instead of x squared, I'm going to have cosine cubed squared, or you could just write that as cosine to the 6th. And then instead of negative x times y, we're going to have negative cosine cubed t times sine cubed t. And then that vector is being dotted with dr. And remember that dr in this context is going to be r prime of t dt. So this is just that tiny piece of path. Unlike in our scalar integrals, we had a ds representing a tiny length of path. So here we have both just the length and the direction. So r prime in this case, you need to do a chain rule here. This would be 3 cosine squared times negative sine t for the first piece, and then the sine cubed one is going to be 3 sine squared t times cosine t, and then that's all dt. Got my vector breaking over to the next line here. Okay, and then to actually integrate this, we would have to first do this dot product. We cannot integrate this if it's still in this dot product form. So we're going to have the integral from 0 to pi over 2. I'm taking this cosine to the 6th times the first component from our derivative. So that's a negative 3 cosine now to the 8th power of t times sine. And then we've got negative cosine cubed sine cubed times that second component from the derivative. So that's a negative 3. We've got a total of 5 sines, so sine to the 5th t, and then a total of 4 cosines, cosine to the 4th t. And this is all integrated with respect to t. At this point, this is just an integration problem. We, I think, can do these integrals. The first one is definitely just a u substitution. If you use u equals cosine t on this first piece, that's a pretty straightforward u substitution problem. The second one's a little bit trickier. If you look at the trig section, so 8.3, or use that trig summary sheet that I posted on D2L, in this case, we're actually going to want to do u equals cosine t, and we're going to split this sine into it, sine to the 5th as sine and then sine to the 4th. And that sine to the 4th, we're going to have to convert to cosines using the Pythagorean identity, so using sine squared equals 1 minus cosine squared. So I'm going to use a u substitution for cosine on all of this. Here's what that would look like. Okay, so I've written this out a little bit. The sine to the 4th here, I'm going to break up as sine squared times sine squared and convert that into 1 minus cosine squared times 1 minus cosine squared. The extra sign in each of these is going to be the du piece, that negative sign. So I end up with a positive 3 u to the 8th from the first piece, and then another positive 3 1 minus u squared, 1 minus u squared, u to the 4th. And keep in mind, all of these u's are coming from those cosine t's. In order to integrate this, we have to multiply out all this u stuff in the second term, so unfortunately, there's kind of a long foiling process here. So this is 3u to the 8th from the first piece, and then 3u to the 4th minus 6u to the 6th plus 3u to the 8th. You can combine the u to the 8th components as a 6u to the 8th, and then at that point this is just a straightforward backwards power rule problem. So applying to the power rule to this, converting all the u's back to cosines, then I'm ready to plug in my bounds. If I plug pi over 2 into all of the cosines, that's all going to be 0. So when evaluating, I'm going to come up with 0 minus, and then when I plug 0 in, all of the cosine pieces are going to come out to 1. So this is going to be minus 3/5 minus 6/7 plus 6/9. And this is not the most pleasant calculation. Maybe just throw this into the calculator. This should come out to negative 43 over 105. So one thing you should be asking is, what does this negative answer mean? This isn't a super big number. This is maybe about half. But the negative means that the work done by this force moving along this path is negative, meaning that the force is kind of pushing in the opposite direction as the motion, at least for part of the path. And again, if you want, you can graph this on the graphing program. It'd be a great opportunity to use that. Graph both the force field and the path. You can graph the path as a space curve with just 0 in as the z component, and the force field you'd graph as a vector field, again with the z component being 0. All right, that's it for this video. Hope this is helpful. Thanks.